Simulators are essential for training in the air traffic control, or ATC, domain to adequately prepare controllers for their tasks at their facilities. The region managed by a single sector of an Air Route Traffic Control Center, or ARTCC, is much larger than that managed by a tower or terminal controller. ATC Simulation Training Technology, or ASTT, is a high-fidelity, web-based simulation tool that is currently under development for use in practicing ATC scenarios. It utilizes an interactive, computer-based system that replicates the actual en route automation modernization, or ERAM ATC system. ERAM is the FAA system that provides ATC services for instrument flight rules, or IFR flights operating inside the en route airspace of the U.S. and is installed at the 20 Air Route Traffic Control Centers. The ERAM system requires coordination between two controllers who both manage the same airspace while looking at two different monitors. The first being the radar position, or R position, which contains an interface with the radar display, and the second being the radar associate position, or RA position, which provides an interface to the ERAM Decision Support Tool, or EDST. ASTT currently supports the following ERAM functionalities: maintaining flight data, including accepting flight plans and updates from controllers; maintaining airspace configurations, including restrictions in effect, letters of agreement or LOAs, and sectorization, the assignment of airspaces to controllers; separating air traffic using surveillance information or other manual procedures; detecting and resolving potential conflicts through the use of medium-term conflict probe decision support tools and tactical alert software, which detect aircraft-to-aircraft and aircraft-to-airspace conflicts; monitoring conformance of flights to flight plan-based trajectories; posting, sequencing, and updating flight information for controllers; accepting and initiating flight handoffs and point-outs with other facilities; aircraft trajectory modeling through the use of kinetic four-dimensional modeling, which provides trajectory prediction for conflict alerts, time of arrival prediction, top of climb, and top of descent prediction, as well as sector boundary crossing predictions; modeling and storing of speed constraints and window vertical constraints by route segment; using aircraft flight envelopes and base of aircraft data, or BADA, for aircraft performance modeling. In order to simulate real-time air traffic for the scenarios, ASTT uses accurate flight dynamic models of several aircraft, each of them including simulated flight management systems, or FMSs, and autopilots capable of steering the aircraft per the aircraft published flight profile. The simulated FMSs are capable of storing flight plans using 4D waypoint trajectories, which include latitude, longitude, altitude, and time constraints. En route scenarios contain several aircraft, usually a combination of active flights and departure flights, the latter of which are activated in the middle of the scenario. The en route controller trainee's job is to handle all traffic within their sector. This includes maintaining separation, coordinating point-outs and handoffs with neighboring sectors, issuing clearances, and responding to any issues, conflict alerts, and other emergencies. For the purposes of training, several tasks are selected for the student to be tested on, and a record of their response to each situation is used for grading their proficiency. A sample scenario has a total of 26 aircraft and test users on events, including point-outs, arrivals, departures, and conflict alerts. The scenario can last from minutes to hours, but usually around 1 to 2 hours, and has events occurring at random intervals in that time frame. This requires the controllers to be alert and focused throughout the period. As an example, at the 5-minute mark, an aircraft that is currently in a high sector right above the trainee's sector of control calls in, requesting a lower altitude. The controller must verify that there would be no conflict with traffic under their control and appropriately accept or reject the request. A minute later, there are 2 events that need to be coordinated simultaneously: a departure from one airport and arrival into another. The trainee is required to assess which one to respond to first and ensure that clearances are issued after the traffic situation has been assessed. 3 minutes after this event, there is a red alert between two aircraft. A red alert occurs when there is an aircraft-to-aircraft conflict with a separation of less than 5 miles and 1,000 feet vertically. This is considered an emergency, and the trainee must change the altitude or heading of one or both flights to increase separation without letting the aircraft come into contact with any other flights in the area. A minute after this, there is a yellow alert between two other aircraft, which occurs when separation is greater than 5 miles, but still within the detection range, which is 5 to 12 miles. This requires a similar rerouting action on the controller's part so that no red alert is triggered. The scenario continues with another arrival 3 minutes after the yellow alert. Then another request for a lower altitude from a high sector, 2 more arrivals, 2 departures, and a red alert and yellow alert. 26 minutes into the scenario, an aircraft is identified as coming into the sector with an inappropriate altitude for direction of flight. The general rule is that all aircraft flying east must do so at odd levels of altitude, and those heading west should fly at even altitudes. The inappropriate altitude for direction of flight requires the controller to update the altitude or give clearance to continue the inappropriate altitude in case of possible conflicting traffic before the aircraft can be accepted into their sector. The scenario ends with 2 more departures, 2 arrivals, 2 alerts, and another inappropriate altitude for direction of flight over the rest of the allotted time. To achieve this goal, ASTT simulation capabilities include spawning of real-time aircraft simulations flying the assigned routes while pushing their surveillance data to the simulated ERAM, replicating the air traffic. Injecting the controller's altitude, speed, heading, and route clearances to the simulated aircraft's autopilot to replicate controller-pilot communication. Automatically performing the adjacent facility controller's actions, such as handoffs and point-outs to the trainee's sector, as well as automatically accepting the trainee's handoffs and point-outs. Providing supervision capabilities for instructors and admins to be able to remotely observe and intervene in the scenario execution by providing web-based sharing of the R and RA windows to authorized users. Providing cross-platform compatibility with different web browsers while maintaining an acceptable performance requirement in displaying the traffic on both windows. Providing an on-screen controller keyboard for both R and RA sides to mimic the behavior of the real controller keyboard without needing an actual keyboard hardware. Providing multi-device displays of a scenario execution, allowing the user to use different devices simultaneously, such as laptops, phones, tablets, etc., to access different views of the same run. For example, the user can use his or her tablet with a touchscreen to display the controller keyboard and use their computer to display the R and/or RA views. Record trainees' responses based on well-defined standards provided by the FAA in handling various ATC circumstances, such as the time it takes to release a departure flight, or time it takes to resolve a conflict, or inappropriate altitude for direction of flight.